we are going to derive another equation of engineering relevance and engineering application. A lot of applications of this equation called the Bernoulli equation, and he is Bernoulli, and this equation relates pressure, velocity, elevation under inviscid flow condition. That is why we are discussing this, okay. Because we are the topic of main topic of discussion is inviscid flow. Under that we discuss flow regimes, so that we know the scope of our discussion, namely high Reynolds number flows. And with first we discussed the Euler equation, now we are discussing the Bernoulli equation. Okay. So, inviscid regions of flow, what we are going to do now is derive the Bernoulli's equation. We will start with the Euler equation. So, that is the Euler equation which I have seen in the previous discussion, and the substantial derivative of velocity has two terms, the local term and the convective term, or the total acceleration is in terms of the local acceleration and convective acceleration. We will restrict the discussion to steady flows. So, we will consider the steady state Euler equation. So, what I have done here is written this rho g vector minus gradient of p on the left hand side, and right hand side we have rho dv by dt, dv vector by dt, and in that for dv by dt I substituted the convective acceleration term alone, and that is what you have here, rho into the convective acceleration. Please note that it is v dot del operating on v, that is a formal way of saying it is not del dot v is divergence. Okay. So, it is dou by dou t. If you recall back the discussion on substantial derivative, and then it is v dot gradient, and that is the operator operating on the velocity vector. Okay. Of course, we do not have this term here, and so it is v dot del operating on v vector. Now, we will use a vector identity. What is the vector identity? You would have come across several vector identities in your vector calculus course. For example, curl gradient of a scalar is equal to 0, that is one vector identity. Similarly, we are going to use this vector identity. We are not going to prove this, it is a little involved to prove this. Even fluid mechanics book take this relationship. So, we are also taking this relationship without proving it. What does it tell you? The left hand side we have v dot gradient operating on velocity, and v dot gradient is the scalar operator operating on a vector. So, left hand side is a vector. Right hand side we have gradient of v dot v. V dot v is a scalar, is a magnitude of v squared, and gradient of a scalar will give a vector. Now, coming to this term, we have del cross v, which is a vector, and once again v cross this vector gives you another vector. So, all the terms in this vector identity are vectors. Obviously, a vector identity cannot have one term as scalar, other term as vector, all of them should be of the same type. So, all the terms here are in terms of vector. Okay. So, the convective acceleration term is going to be expressed in terms of the right hand side of this vector identity. Okay. So, let us do that. Okay, that is a vector identity. Now, what we will do is let us try to understand this del cross v, which is well known to you. It is the curl of the velocity vector, which is a cross product of the gradient vector and the velocity vector. Okay. That should be well known to you from a calculus course. Now, let us express that in terms of variables which you have come across in this particular course. Okay. So, you know the cross product can be expressed in terms of this determinant. the first row is I j k, then we have dou by dou x, dou by dou y and dou by dou z representing the components of the gradient vector, and then the last row represents components of the velocity vector. Okay. So, now let us expand this determinant. So, the first term we have dou v z by dou y minus dou v y by dou z and of course, the I vector. Then second term we have dou v x by dou z minus dou v z by dou x and then j, and then for the next term we have dou v y by dou x minus dou v x by dou y and then k vector. Okay. Let us multiply and divide by 2 and you will see something familiar to us. What is that we have done? Divide every term by 2 and multiply by 2 and taken out 2 outside. Now, if you look at the terms here, it should sound something familiar to us, especially the last term, because usually we have been working on the x y coordinate. What does it represent? That represents the rate of rotation in the x y plane. Just to recall, we express the velocity gradient tensor in terms of the strain rate tensor and the rotation rate tensor or rate of rotation tensor. And look at this, what we have here is one of the components of the rotation rate tensor. Of course, we know that this is omega dot x y and this is minus omega dot x y. Okay. And so, what we have here is omega dot x y. Similarly, you have these terms also represent the rate of rotation in the different planes, okay. And that is what is shown here. This figure should be familiar to us, which we discussed when we discussed strain rates in fluid mechanics in fluids, and we said this figure shows a fluid element at time t and then t plus delta t, and we said a fluid element can undergo normal strain rate, shear strain rate and rotation rate, and that rotation rate is what we are discussing now. This component, this term represents that rate of rotation. Okay. So, let us use that. So, 2 into, let me explain the last term first, then you will become clear to you. So, this term represents omega dot x y, rate of rotation of fluid element in the x y plane. Similarly, y z plane and z x plane. First two terms may not be very familiar to us, because usually we have been working in x y coordinate, but moment you understand this term to represent rate of rotation x y plane, then you can easily extend and write the first two terms. Okay. So, now you have a vector. Now, how is the vector formed? The vector is formed with the components as the rate of rotation in the y z plane, z x plane and x y plane. Okay. Such a vector we have used omega, bold omega to represent vector and then dot. Okay. So, let us give names to them. So, omega dot is the rate of rotation vector. Usually fluid mechanics book may call us just rotation vector. To be in line with our nomenclature, we will let us say call as rate of rotation vector. Okay. And vorticity vector is twice the rate of rotation vector. In short, what we are discussing, to summarize what we have discussed so far, what we did was we use this vector identity and express the convective acceleration term as sum of two terms. In that we had one del cross V term. We know that del cross V is the curl of V, and we started with the determinant expression, expanded that and found that the components of the del cross V vector are nothing but the rate of rotation of the fluid elements in the 3 planes, and that del cross V has now got a significance of twice the rate of rotation vector. So, we denote that by the vorticity vector. So, let us do that. Left hand side is the convective acceleration term, and right hand side we have this term gradient of V dot V, and I am replacing del cross V, the curl of V, with the vorticity vector. So, whenever you come across del cross V or rate of rotation vector or vorticity vector, this tensor should come to your mind, where we have discussed all the components as the rate of rotation in the respective planes, and this diagram should also come into your mind, which includes of course normal strain rate, shear strain rate and rotation, but now this discussion is confined to the rigid body rotation. Remember, the fluid, this rotation tells about the rigid body rotation of the fluid element. Okay. Now, let us proceed further. Okay. So, this is the steady state Euler equation, where we have taken only the convective acceleration, okay. And we discussed the vector identity. We are using this vector identity, and just now we discussed that this del cross V can be represented in terms of the vorticity vector. So, now let us substitute this vector identity in terms of vorticity vector in the right hand side of this steady state Euler equation. So, what is that we have done? We have taken this V dot gradient, that operator operating on the velocity, that has been the convective acceleration term is replaced using this vector identity, okay. And that is why we have here a gradient of V dot V, and then we have V cross the vorticity vector, of course multiplied by rho, okay. Now let us take this gravity vector and let us try to express that in terms of a gradient, okay. Okay. G vector, okay. Now to do that we should discuss the choice of coordinate axis. The obvious choice of coordinate axis whenever there is elevation is this coordinate axis, where z is along the vertical direction. So, G vector can be written as minus G k vector, because G acts along the negative z axis. Now, k can be written as gradient of z. How is it? Look at this, what is shown here. Gradient of z is dou z by dou x I, dou z by dou y j, and dou z by dou z k. So, these terms vanish, and this is unity giving us k vector. K vector can be written as gradient of z, and that is what is shown here, minus G gradient of z. Now, G is a constant, you can bring inside the gradient operator, and so I write as minus gradient of G z. Okay. So, let me just quickly repeat. What we are doing here is expressing the G vector in terms of gradient of some variable. G vector is minus G k vector, k is gradient of z, G is a constant you can bring inside. So, it becomes minus gradient of G z. Okay. Now, let us substitute this in the above equation. So, G vector is replaced by minus of gradient of G z, and then of course, we have minus of gradient of pressure, and then what I have done here is brought this term to the left hand side. So, I have minus rho, and V dot V is of course the magnitude of velocity squared, V squared, of course I have taken the 2 inside, and then right hand side we are left with minus rho V cross the vorticity vector. Okay. So, taken this equation, 2 things have been done. G has been expressed in terms of gradient of g z, and then this term has been taken to the left hand side and v dot v has been expressed as velocity squared. And that is the reason, see, we have gradient of p here, we have gradient of v squared by 2, that is why g vector is also expressed as gradient of g z. You may be wondering why express g in terms of a gradient of g z. This is the reason that you have gradient of pressure, you have gradient of v squared by 2, and so we also like to express g vector in terms of gradient of g z. Okay. Now, what we will do, we will divide by density, and then I can divide, if you look at the terms, I can divide this by density, I can divide this by density, similarly I can divide right hand side also by density. But when I do here, I can divide by this by density, but I make another assumption that density is constant, which means that it is incompressible fluid. So, the way in which I am going to express is, I am going to, I have gradient of P divide by rho, I assume density is a constant. So, I bring the rho inside the gradient symbol, that is what has been written here. Okay. And of course, the negative side cancels on both the sides. So, we have gradient of P by rho, then we have gradient of v squared by 2, then we have gradient of g z, and right hand side we have v cross the vorticity vector. Okay. So, the previous equation minus sign cancels out, divide by rho and bring, moment I do this, or this can be done only if I assume incompressible fluid. Okay. And that is what has been done here, we have written as gradient of P by rho. Okay. So, now let us proceed further. Now, what we are going to do now is the previous equation, take a dot product of each term with a differential length ds vector along a streamline. Okay. What is shown here, this figure is from our discussion on streamlines, same diagram has been shown here, where if you recall back, streamline was defined such a way that at any point if you draw a tangent, you get the velocity vector. Okay. Now, we are considering a differential length ds vector, and in our earlier discussion on streamlines, that differential length was shown as dr vector. Now, we are using ds vector, because I am following derivation from this book Munson, and s can also mean s vector along this streamline. Okay. This dr vector and present ds vector both have the same physical significance, only nomenclature is different. Okay. Now, because the it is a differential length, it is tangent to the streamline. So, the velocity vector is along the ds vector. Okay. So, what is that we are going to do now? Take the earlier equation, take a dot product of each term with the differential length ds vector along a streamline. Okay. Let us do that, and remember that ds vector is along the velocity vector. Why is that? You have differential length along the streamline, which means it is tangential to the streamline, and we define streamline in such a way that if you draw a tangent, you get the velocity vector. So, ds vector is parallel to the velocity vector. Okay. What is this equation? The previous equation, we had these terms in the previous equation, every term has been dotted with the ds vector, that is what has been done. Okay. Now, let us see what happens to the right hand side, having dotted with the ds vector, let us see what happens to the right hand side. Okay. To understand the right hand side, we will have to focus on this figure. What is shown here? A velocity vector and then the vorticity vector. They can be in two different directions, okay, because one is velocity vector, other is the del cross velocity vector, the curl of velocity vector. So, this velocity vector and this vorticity vector. Now, we have one v cross vorticity here, and that is vector is shown here. We know that when we take cross product of two vectors, the resulting vector is perpendicular to both the vectors. So, in this case V cross the vorticity vector, that resulting vector is perpendicular to both V vector and vorticity vector. So, let us write down that V cross vorticity is perpendicular to both V and vorticity. Why is that? Suppose I have A vector and then B vector, and if you take A cross B, that vector is perpendicular to both A vector and B vector. Instead of A and B, here we have V vector and vorticity vector. So, the cross product between V vector and vorticity vector is perpendicular to both V vector and the vorticity vector, and that is what is shown here, that is what is written here. So, now we have seen the ds vector and V vector are parallel, just now we have discussed that. So, what does it mean? This V cross vorticity is perpendicular to V vector, but this V vector is parallel to the ds vector, which means that this V cross vorticity is perpendicular to ds vector, okay, and that is what we write here. V cross vorticity is perpendicular to ds vector. So, let me just repeat once. V cross vorticity, the velocity cross vorticity is perpendicular to both velocity and vorticity vector, but velocity is parallel to ds vector, or ds vector and V are both parallel, either way we can say, which means that this is perpendicular to ds vector, okay, which means that the right hand side is 0. V cross vorticity, that vector is perpendicular to ds vector, which means the right hand side is 0. That is why we took a dot product with a differential length along a streamline, okay, is equal to 0 on the right hand side. Okay. So, now the right hand side vanishes. Okay. Now, let us take the left hand side and see what happens. Now, here we express the dr vector in terms of dx I, dy j, dz k. Similarly, the ds vector is expressed in terms of dx I, dy j, dz k. Okay. And now, let us try to evaluate the first term here, okay, first term on the left hand side. Instead of evaluating gradient of p by rho, let us for the moment take gradient of p dot ds. Okay. So, what is gradient of p? Dou p by dou x I, dou p by dou y j, dou p by dou z k. Now, let us take the dot product of gradient of p with ds vector. What do we get? We have dou p by dou x into dx and dou p by dou y dy, dou p by dou z dz, which is dp. Okay. So, when you take dot product of gradient of p with ds vector, you get dp, okay, which means that for this term you should get d of p by rho. Okay. So, left hand side, the first term becomes d of p by rho, second term becomes d of v squared by 2, and next term becomes d of g z, right hand side is 0. So, now of course, it becomes much simpler to read. So, first term, what you have demonstrated here, what you have shown here is for gradient of p dot with ds vector. What we have there is gradient of p by rho dot with ds vector. So, this becomes, the first term becomes d of p by rho, d of v squared by 2, d of g z is equal to 0. Now, let us rewrite that and write this as d of p by rho plus v squared by 2 plus g z is equal to 0. What does it mean? Okay. We have taken a small length, differential length along the streamline, which means that we are at 2 points. The 2 points are along the streamline, slightly separated on the streamline. We are not considering any 2 points, please keep that in mind. We are taking 2 points, let us say one coordinate is x, y, z, other is x plus dx, y plus dy, z plus dz, but these are not any 2 points which are adjacent to each other, those 2 points are on the streamline itself. So, and they are differentially separated. This tells you that the difference of this quantity when I say quantity, sum of these 3 terms is equal to 0 between those 2 points. So, if you are on a streamline and if you consider 2 points adjacent to each other, the difference of this value between the 2 points is 0. What does it mean? That particular summation is a constant along the streamline. Okay. So, P by rho plus V squared by 2 plus G Z is equal to constant along a streamline. Those terms should be familiar to you. The first term is pressure energy per unit mass, and then the second term is kinetic energy per unit mass, very familiar to us. Third term is the potential energy per unit mass is equal to a constant along a streamline. What is this pressure energy? This pressure energy represents the work done by the pressure force in moving the fluid through a distance. Okay. It is also called as flow energy. Either you can tell as pressure energy, also as flow energy, because that represents the work done by the pressure in moving fluid over distance. We will come across this term once again, energy balance. Of course, all these are different forms of mechanical energy. When you say mechanical energy, what does it mean? Complete conversion to mechanical work should be possible. If you have thermal energy, that cannot be completely converted to mechanical work because of the second law of thermodynamics. Okay. But these forms of energy are called mechanical energy because complete conversion to mechanical work is possible. Okay. So, that is why the Bernoulli's equation is a mechanical energy balance. Sometimes this equation is divided by G and written as the pressure head and the velocity head and then the potential head. Okay. That is also done. Okay. And so, this tells you, Bernoulli's equation tells you that the sum of these energies, pressure energy, kinetic energy, potential energy, of course, all per unit mass is a constant along a streamline, okay, not anywhere between any 2 points in the flow field. Okay. What are the assumptions? Let us recall the assumptions. Inviscid flow, because we started with the Euler equation. We started with the steady form of Euler equation. So, we have also assumed steady flow. Then during the derivation we assumed density to be constant. So, which means we assumed incompressible fluid. In fact, not only incompressible fluid, remember when we discussed continuity equation, it is applicable for incompressible flow also, which means that the equation what I derived is not necessarily for, let us say, water, it is also for flow of air at low velocities. That is why we define incompressible flow and along a streamline. Okay. So, the Bernoulli's equation tells about the sum of these 3 energies is a constant along a streamline, steady inviscid flow of an incompressible fluid, and this along a streamline, where did that come from? Remember, we wanted to make the right hand side 0 where we had a vorticity term, where we have the rotation term. Okay. To make that 0, we had to consider this balance along the streamline, okay. And that is why this restriction comes from, that is where this restriction comes from.